Okay, it's a new unit on graphing. Now, first for perspective, we are about to do what in my regular pre-calc class we would do over the course of about 3 days. You're going to do in 1 day here. Okay, so this gets pretty intense. You got to be able to pay attention and take good notes. You can do it. I know you can do it, but we usually take our time in teaching this in regular. We don't have that time. So you will learn a lot more things here in honors, and that comes at a price of having to go pretty fast. All right, first of all, this is not exactly like the unit circle because it's got all that stuff inside it. That's for doing some graphing later called polar graphing. We're not going to do that today, but I just wanted to kind of show you what that graph looked like. We're going to do a lot of graphs on this type of a graph, and so generally speaking, do not copy this down yet because I'm not ready yet. Oops. Generally speaking, the sine graph makes kind of a wave like that. Do you get it oscillates back and forth where it hits 1 and then goes down to -1? It just keeps going forever. All right. So if we were to look at sine, a nice clean graph, it would go something like this. Up, down, and just continue forever. And then it does the same thing in this direction, continues forever. So that's the graph of sine. I'm going to give you all the major parent functions today. I shouldn't say all of them. It's sine, cosine, and tangent, the 3 that I'll hit today pretty hard. And then tell you about moving them around and stuff. So everybody copy down this part of the graph. And we need to label the parts. All right, what's the highest that sine ever goes? A lot of you guys know this. Biggest number you ever wrote, 1. How about the lowest that ever went? -1. And we usually did that in a different context, though. We did that on the unit circle. I'd like you to just take a moment and remember, where the heck was 3 pi over 2? And if you found it, what would the sine of 3 pi over 2 be when you got there? Do you agree that 3 pi over 2 is down here? And that spot is at something comma something? Because we can't draw a triangle there. 0 comma -1, excellent. And then at 0 comma -1, I now know the sine and the cosine and the tangent. Remember these? Sine is which one? Sine's y. Cosine would have been x. Okay, so this is the sine of 3 pi over 2. And it is -1. Now I want you to look at this graph. Do you see where it hits -1? Do you get that this must be 3 pi over 2 then? But it is. This spot right here and this spot right here, this is 2 pi. This is 0, of course. This is halfway, so it's pi. And this is halfway to pi, so that's pi over 2. Those are the 4 major spots that you have to label. 0 is pretty obvious. These 4 are the 4 major spots. Now, I happen to just call out that one because it was where it was -1, but that's not like a special spot on this graph. I'll just move that period over there somewhere. All right, do you have this copied? This is very important. This is sine, because if you don't get this, then when we stretch sine and move it and flip it and do all that kind of stuff to it, you won't have a clue if you don't know what the original one looks like. Okay, so now let's say that I wanted to make this go twice as high. Well, there's 2 options. I can go like there. I just made it go twice as high and twice as low. Or I can relabel this and say, now it's not going to 1, now it's going to 2. Now it's not going to -1, it's going to -2. Do you get how I just didn't have to even redraw my picture? I could just relabel it. All right, so that's how we do it if we put a 2 right there. That's my first thing. That's called a vertical stretch. Okay, now I want to give you a little bit of context. Do you remember back to these good old days? Do you get how this one has been moved and stretched and that kind of stuff? Does this ring a bell? And the stuff on the inside, it's high vo, horizontal stuff is on the inside, and vertical stuff was on the outside. So this is a vertical stretch. This is a horizontal shift. Remember all that stuff? Just trying to relate what we're about to do to the sine function with all of these. This would take my parabola and move it where? What does that mean? Down 7. So my whole parabola, wherever it was, gets moved down 7. All right, well, we're doing the same idea with our sine functions, and this is where you'd get a vertical stretch right there. And then if I put something in here, I'm going to get a what kind of a change? Horizontal. Okay, so here's a typical horizontal change. Y equals 2, got a vertical change, sine of 3x. Do you get, I just messed with the horizontal, but I don't want to have to redraw my graph because that's going to be a real pain. So we let you just relabel your horizontal axis. Now, we need to know what this is, though. Do you get that's a horizontal stretch or shrink? Shrink. Factor 3 or 1/3? 1/3. So we're going to multiply everything by 1/3. Now, what just happened there? We just, instead of making you redraw the graph and have it shrink 3 times narrower and having the graph kind of look like this, those can be really hard to do. Relabeling it is really easy. Do you get now? It doesn't end at 2 pi anymore. It ends at 2 pi over 3. It finishes up its cycle. Okay? And that's called its period. The period of the original one, it ended at 2 pi in the first place, right? This one now ends at 2 pi over 3. The whole cycle, to start it and finish it, takes 2 pi over 3. It's like time, because this is normally like what time is, except in this case it's angles. All right, going kind of fast here. I want to back off one and just say, what if then they had this? Do you get, it's not just a parent graph, it's been stretched and stuff? All right, would you start, please, by ignoring the 7 and the 2 and just graph the parent one and label it as if it was just the parent one, and then we will go back and tweak it so that it's right for the stretches and stuff. So start by just graphing the parent. I know you might already have one. Don't just use the one you already drew. You need to practice. Try to draw the wave correctly. And I'll pause for a second while you try that. All right, so the original would have gone like this and would have hit a high of 1 and a low of -1. My high might be going up a smidge too high, but anyway, I think you get the idea. And then it ends at 2 pi. So normal period of these things is they finish up at 2 pi. With me so far? Right, then I can take half of 2 pi, and that's pi. And then I can take half of that, and that's what? Pi over 2. And then what's in between pi and 2 pi? 3 pi over 2. It's almost like those numbers that were here, 0, pi over 2, pi, 3 pi over 2, and 2 pi just got put in a different spot. They got kind of unwrapped, opened up out onto a straight line here. All right. Now, that 7 needs to be handled. Oops, sorry. That 7 there needs to be dealt with. All you got to do for that one, though, is really easy. Is times this by 7 and times this by 7. So this becomes -7. And this becomes +7. Raise your hand if you had that part right. Okay, good. Now the other part. This 2. It does not make it twice as wide, otherwise we would have times everything by 2 and that would become 4 pi. Instead, it's the stuff on the inside is always the opposite of what it seems, so it's multiplying everything by a half. How many of you knew to multiply everything by a half? Excellent. Then this became pi over 4, pi over 2, 3 pi over 4, and pi, because the 2's would cancel. Now what's its period? It's not 2 pi anymore. It's pi. You can just look right here and see, finished up in pi. There's a little formula for that. The period will always be 2 pi unless you have a number here, right? And that's the spot that we call B. So it's 2 pi, and you always then would multiply by 1 over B. So that's putting a B on the bottom. So there's a formula for that, 2 pi over B. Again, all it means is, if this is the B term, that whatever that B term is, you're going to multiply by 1 over that B term, which is like dividing by the B term. Here, and here, and here, and here. All right. So far, we haven't ever moved it. Forget how the original graph is still there. We didn't ever actually do anything. When do we actually make it do something? When we make it shift. Let's say I wanted to move it to the right a little bit. Do you get that I'd want to do like minus something then? Let's say I went minus, and these are in like pi over 2's and stuff, right? Pi over 2. That seems like I just move it to the right, pi over 2, which is this far with my new numbering system. See, that's pi over 2. I'd have to move the whole thing over that far, so I'd grab this, move it over. All right, but it's a little more complicated than that. That tells you to make everything one, all the numbers have to be renumbered on that graph, and they all get multiplied by a half. This was the B term, this was the A term, and now this is called our C, and then take a wild guess where D is on the outside. Let's say I say plus 1. That's our D term. That's A, B, C, and D, okay? But one of my favorite sayings comes into play once again. If you can factor it, you should. So that can be factored. The B won't change because the 2 will come out. The B will still be 2. But the C term will change, and that's one of the most common mistakes here is kids forget to factor it. They think you should move it over pi over 2, which is also known as 90 degrees, but you shouldn't. So if I factor that 2 out, and I now have x minus, what do I put there? Can I just put pi over 2? No, because then if I multiply it back out, I got 2x, and I got, the 2's would cancel, I'd have pi. Pi over 4 is correct. Do you get now, when I multiply 2 times pi over 4, it'll equal 2 pi over 4, which will give me what I want? Negative pi over 2. All right, so I just factored that now to y equals 7 sine 2 x minus pi over 4. And then there's a plus 1 here. Do you get that's just going to change my y-axis labels from being 1 and negative 1 to 7 and negative 7? That'll be easy. Okay, this, you're going to go through and multiply all these numbers by, what do you multiply by with that 2? Nope, no multiply them by 2. Multiply them all by 1/2, okay? And then we got to move the thing, what is that? Right or left? Right. And then what is pi over 4? Do you remember how many degrees that is? 45 degrees. Or pi over 4 on your graph. If you happen to have a pi over 4, it's really easy to tell, oh, it's that far. But sometimes you have to like deduce how far pi over 4 is. And then what is this plus 1? It just moves the whole graph, which is a wave. It moves that whole graph up 1. Boop, there. Just moved it all up 1. Can you hit the door for us, please? All right. There. Taught you everything that you have to know except I only taught you what sine looks like. So before we move on, I want to do one culminating like problem, like, okay, here's how it would look, and here's how you should do it. But I'd actually like to do it in your homework, because we have enough homework problems for tonight that I'll just do one of your homework problems with you. But at that moment, you will think you're all ready for the rest of the assignment, but you're not, because you don't know what cosine looks like, and you don't know what tangent look like. All right, so I got to teach you those things before we're done today. So I'm going to pause for a second while we get to the homework. Okay, so here's our homework start. It's day 1. And the top one is as easy as it seems. I want to do it with you right now. I only have one little change there. I just talked you through the most complicated ones, or almost. There's one more thing, but we don't need it till tomorrow. So this one's just normal. Don't even look at the 3 yet. Just do normal sine, and then we'll go back and fix it and reflect the fact that it's been stretched. But just do normal sine graph. Now, here's my advice on these. I go up 4 marks and make that 1. I go down 4 marks and make that -1. And then I go over 4 marks and make that your first hash mark, over 4 more marks, over 4 more marks, over 4 more marks. There's a missing mark in there, but it's like there to keep it equal. And again, I'm not going to be super picky with you. These pieces of graph paper kind of suck, so just do your best with them. And there's a missing mark right here if you really want to know. Anyway, so now we need to put our little sine wave in there. Goes up, comes back down, goes down, comes back up. There. There's our sine graph. Except we got to label all those spots, and we got to stretch it because there actually is a 3 in there. But one thing at a time. This spot, 2 pi. And then I like to go to half of that. You see where halfway to that is? That's pi. And then half of that, pi over 2. And yes, there is a 0 back here. And then what's this spot in here? Hardest one to remember. 3 pi over 2. Awesome. There, now that's original sine. Kind of like original sin, but different. All right, original sine graph. Now, what do I need to do to change it? You're right, you guys need to work on that. So go ahead, here's your stuff, and I want you to take those 2. Okay, so let's wrap this thing up. This 3 right here tells me that this just has to turn into a 3 and a -3. Technically, I was multiplying by 3, but good. Now I'm done, except I haven't answered all the questions on here. All right, what was the A? Well, think of it this way. The first number in front, that's the A. The B would be right there if there was a B. So if there isn't any B, does it mean the B is 0? No, it means the B is what? 1. All right, so then that's 3. That's 1. Okay, what's C? Well, is there anything in here that's being added to the X? No, so you can think of it as the X is being added to 0. Would you agree the C is 0 then? I know that feels weird because the last time we made it a 1, but you would have been adding something if there was something in there. And do you get that the D would be whatever you add at the end, which again, there's nothing there. So I could say it's 0. 3, 1, 0, 0. Does that make sense so far? Okay, now let's answer the other little questions. The amplitude of a normal one is 1. What's the amplitude of this one? 3. That's the amplitude. All right, by the way, if it's ever negative, an amplitude is how high it goes. You never would say -1. The amplitude would just be 1. If it had been a -3 in front here, the amplitude would be +3. You take the absolute value of it to get the amplitude. All right, the period. I would just wait till you're done with the graph and then look. How long does it take to complete? 2 pi. Do you get if we would have changed this by dividing everything by 3 or something, it might have ended at 2 pi over 3? It's kind of like saying, where did it end? Where did it wrap up a complete cycle? So the answer to that one is 2 pi. And no, it's 2 pi over b is the formula, and our b is 1. So it's 2 pi divided by 1. So it's just 2 pi. And the horizontal shift, there was none. And the vertical shift, none. You with me so far? Okay, I know you can do the next one, but don't, because I now need to go and teach you what the graph of cosine looks like. They're different. Very similar, but different. Okay? What I will do is go through and tell you which problems you should skip and do on this assignment. Okay? We're doing all the ones on the front page here. Then we're going to skip this entire orange page. There's enough stuff coming. I think we can skip this whole page. Look, I did a sine wave. On to this page. Let's cross off this one with a sine wave. This one, I think you should do a couple of these, but not this top one. Cross that one off. I think you should do 90 and 91. And I think that's it, so we can skip this purpley one. All right, so that gets you down to what I feel is a normal size assignment or reasonable size assignment for today. But you need to know how cosine looks. So everybody, get to a blank page right near where you made sine, and here's cosine. It is very similar, but it does not start at 0 and go up. Like, here's what sine would look like. It's not the same, but it's a lot like it because it starts at 1 and then cycles back and forth between 1 and -1. So it starts at 1, goes down, turns the corner, ends at -1, comes back up again, and then stops there. I like to think of it as a valley. You start on the mountaintop, you go down in the valley, and then you come all the way back up to the other mountaintop. Okay? That's cosine. And it's got the same exact wave shape. In fact, if I continue this a while, you might get this pattern. Do you get that that's what sine looks like, this blue one? It's just shifted over. It's just sine shifted. That's why cosine really isn't anything new. It's just sine except shifted. And tangent really isn't anything new because it's sine divided by cosine. I'll show you what tangent looks like just briefly, but for right now, let me get this out here. There. This goes to 1 and -1, just like the other one. And it's got 4 markings, just the same. It ends at 2 pi. Halfway is pi. Half of that is pi over 2. And half of that is 3 pi over 2. So there you go. If this was cosine except stretched or whatever, you'd always start like this. And then let's say I put an 8 right here. What's that going to do? Change these numbers to what's? 8 and -8. Good. And then if I wanted to throw in a b term of like 2, then it does not make it twice as big. It makes it 1/2, 1/2, 1/2, 1/2. Following this? Making sense? Okay, good. Then the last kind is, what if it's shifted? Let's say it says 2x minus pi, for instance. What's my favorite saying? If you can factor, you should. So you factor that out. You get the 2 out, and what would you have left? X minus pi over 2. Very good. And then that tells you you have a shift to the right of pi over 2. So how do you move this whole thing to the right, pi over 2? Well, that's where pi over 2 is. From 0 to there, it's that far. That's how far we should shift it. So I grabbed this and I shift it over. There. I moved it over. Pi over 2. See how far I moved it? That far. Because that's how far pi over 2 is. Was here. There, I moved it over. Pi over 2. Okay? All right, there's more things you can do to them, but for right now, that's all you need to know for today, and that's cosine's graph. I told you I was going to tell you tangent. Let me tell you, it's weird. But if you know that tangent is really sine over cosine, do you get, here's sine, and here's cosine. Ooh, this is hard to do on the same graph. Then tangent is always any point you pick, like let's say I pick this spot right there. Tangent at that spot would be the, well again, this is the sine, and this is the cosine. Do you get where cosine is 0? You'd have it undefined, exactly. So wherever cosine is 0, which is here and here, there's asymptotes. And if I keep going with my graph, it goes forever to the left and right. There's another one here. And tangent ends up looking like this. Notice, sine is 0. Well, then the top part's 0. Do you get the top part 0? 0 divided by anything would be 0. So whenever this blue one hits, sine has to be, or tangent has to be 0 wherever sine is 0. All right, so now that's really, really messy. Let me just clean it up for you. I just wanted to show you why, instead of just saying, here, trust me, this is how tangent looks. I showed you why there's those asymptotes at least. It was where the bottom part, since it's sine over cosine, it was where cosine was 0. That's why there's asymptotes there. And this is at pi over 2, and this is at negative pi over 2, and that is your standard graph of tangent. So, its period, it does not take as long to finish. It finishes up in only this far. So that, when you take the positive a half and the negative a half, makes 1 pi. Its period is pi over b, because its period is shorter. It just gets done quicker. The graph is finished over the course of just this far, which is negative pi over 2 to pi over 2, which is a total of 1 pi. All right, that is as much as you need to know. Now let's get to your homework again and find this page. No, this page, sorry. Come on, there it is. Let's do this number 2 together. Remember, go 4 marks in every direction. For this type of graph, that's what looks best. There. Then, it's sine still. Sine starts at 0. I think it's best to think of these as having like 4 parts to them. You go up with a curve. You go back down with a curve. You go all the way to the bottom with a curve. And you go all the way back to the top with a curve. So there's sine, and I should label this 1, negative 1. That's 2 pi. That's pi. That's pi over 2. That's 3 pi over 2. I strongly recommend you always start with the original and then go back and look and say, okay, let me think now. 3, what's that going to do? Horizontal shrink. So I don't use 3. I multiply everything by 1/3. So 1/3, 1/3, 1/3, and 1/3. So that's 2/3 now. So, so I know its period. Its period isn't 2 pi anymore. It's 2 pi over 3. Was this one ever horizontally shifted? No. Because there was nothing in here, like it added 0 in there. Plus there's a 0 on the outside, so that tells you horizontal and your vertical shifts. And this is A, there's nothing there. Well, and that means there's a 1 there. And this is B, and this is C, and that's D. Okay. Now you got to do it for cosine. If hopefully you took notes on what cosine looked like. Always start with the parent graph, tweak it from there. All right. When you get to this page, it adds in some shifts, and what's the negative in front going to do to it? Flip it. So if the graph for sine normally looks like that, do you get flipping it will cause it to look like the blue one? That's flipping it. What's up at 1 becomes down at negative 1. Flips it because you're multiplying by, it's like multiplying by negative 1 there. Okay, so that's how you flip a graph. And side note, interesting factoid, an interior flip, if there's ever a negative on the inside, it actually does the exact same thing as a vertical flip. A vertical flip and a horizontal flip do the exact same thing. So if I had a negative in here, it was negative all that, negative right there, it would cause it to take the normal one and flip it this way, even though that's the horizontal like type. Horizontal flips and vertical flips look exactly the same on sine. Okay, that's all I need to know. And I know that was a really intense day. Tomorrow is mostly review, thankfully. So your life won't be that bad tomorrow. Tomorrow will be a lot like today, except you already know a lot of stuff. Yes, sir. Excellent question. I don't know. So first to third for MCAs. How many of you are going to be in that MCA situation? All right, so that does hit this hour. All right, so a lot of people are also going to be just absent. I will have a video up. Watch the video. Really, really worth it. Stay caught up. You don't want to fall behind and then all of a sudden the test will jump up on you. Next 12-minute left. Warning there. Test is coming next Wednesday. So basically a week from today, you got the test on this stuff. We kind of go pretty fast in here. At least we took it extra couple of days on that proving thing. I think probably was a good idea because you guys rocked that test. I haven't graded all of them, but overall, you guys agree that was a little bit easy? All right, good. Last year, they would not have said that. Last year, they would have said that was one of the hardest tests they've ever had because we added those extra couple of days and made it easier. You did extra practice. So, all right. And last year, we'll let them have a partner for the whole test. So anyway, and they still said it was a really, really hard test. So anyway, overall, I think that was a good use of a couple days. If we feel the same way about this week, we could extend this week, but we don't have unlimited days to just push it because what we're doing is shrinking how much time we have for vectors, which is the very last unit that we do. But last year we thought we had too many days for vectors. It was okay to take off a few days. So, all right. That's all I got for you for the video for today.